Okay, great. Hi, so I'm Phil Miller. I'm an alum of PPL also. I finished my PhD there in 2016, for those of you who are newer than that, and then worked at CharmWorks through the end of 2017. So today I'll be talking about the design and implementation techniques for an MPI-oriented asynchronous many-tasking runtime from the Dharma system. So the team of people currently working on this code base is listed here. There's another, I think, half dozen or so who've previously contributed to the system and moved on to other projects as well. So this is a big team effort with a wide range of contributors from Sandia and contractors from outside the lab as well. So Dharma is a toolkit of libraries to support incremental AMT adoption in production scientific applications. So what that means is that our target audience, kind of riffing off of what Professor Kaiser said a few minutes ago, is particularly the simulation authors, the developers, at places like the national labs and universities who have deep familiarity with writing MPI-based code, but recognize some need for an AMT system for reasons of excessive synchronization in their algorithms or load balancing, or from what we found, other motivations can sometimes sneak them into this direction as well. So the core module of the Dharma system is VT, which stands for the virtual transport. Excuse me. So this is an MPI-based implementation of an asynchronous runtime system. So we've strived for extreme portability here, rather than trying to attach to the lowest level network layers on any given machine. And it's written using C++ 14 only, with some concessions to certain compilers that don't quite accurately implement the standard or have bugs in their implementation, but that are very popular among real machines and real users. So we've preferred to accommodate them rather than to say, no, everyone has to upgrade their compilers. So split out from VT is this checkpoint library, which for those of you familiar with Charm++, is comparable in some ways to POP, but we believe we've made some interesting improvements to it that we'll discuss later in the talk. There's a tiny support library called Detector that we use for checking various type traits in the within the runtime regarding user classes and messages and so forth. There's a load balancing analysis framework, which I won't get into in this talk, but I will discuss in mine later this afternoon. And there's a checkpoint analyzer, which we kind of treat as a sanitizer of sorts for the sort of code that's necessary to make all of this run. So I'll discuss that later in this talk. So here's a quick outline of our talk. We'll start with the motivation for developing our runtime rather than using one that's already in existence. I'll go over particular implementation ideas that have supported development of this runtime system and helped us achieve our goals. And also might just be cool ideas for people here to see and learn about. Talk about some of what we've done with serialization, give some preliminary application results. So first, the motivation for our particular development and for doing this in a fresh environment rather than trying to use something that's already out there. So MPI is kind of the dominant paradigm of distributed memory parallel programming, and it tends to go hand in hand with a single program, multiple data style of implementation. So there is a very deep ecosystem built up around MPI of developers, training materials, courses, experiences, There's implementations of MPI on every supercomputer and cluster platform in existence. That's typically one of the purchasing requirements, that vendors have to provide good working MPI on the system, or it's not accepted. There's millions and millions of lines of code of applications and libraries. There's integrations with the execution environment. So all of the srun and bsub and MPI exec and so on that get jobs from the user's scripts to actually running on the big parallel distributed machines. There's lots of development tools for debugging and performance analysis, lots of research literature, and so on. So in our particular development context, the entire suite of applications from Sandia National Labs are developed on top of very large MPI libraries and toolkits, such as Trilinos, which contains solvers and distributed data structures and so on, STK, the Sierra toolkit, which supports unstructured and structured meshes, and a whole lot else. And there's basically no chance that a code base like that is going to be rewritten in much of any fashion. So instead, we've decided that the best approach is to consciously coexist and provide a transitional AMT runtime implementation that can make it straightforward to demonstrate incremental value to developers who adopt it. So to support that incremental adoption, we maximize our attempts at interoperability and embedding. So the expectation is that different parts of an application might all be initially written in MPI, and when AMT adoption comes into the picture, over decomposition or just expression as asynchronous algorithms can happen in small steps, one part of an application at a time. And that then means that there's going to be transitions between MPI execution and AMT execution, or SPMD and AMT execution, possibly many times per time step. And so that implies that any sort of context switch or handoff of control flow between them has to be very inexpensive, because we expect it to be very frequent. So for domain developers of particular science or engineering applications, our AMT actually exposes a lot of its basic constructs in an SPMD, often collective form, especially for things that individually are not going to be performance sensitive, but do need to be part of the programming interface. So a lot of initialization and setup kind of code. For simplicity, we just say, yes, you can write that in your traditional SPMD and not think too hard about it being part of an asynchronous distributed algorithm. We've also chosen not to dive into on-node parallelism directly, but instead to coexist with the diversity of on-node techniques, including CUDA, OpenMP, COCOS, and so forth. And we actually have plans for how we can directly integrate our distributed programming model with the asynchrony that some of those on-node techniques can expose. And we also have actually developed a new asynchronous distributed protocol to safely interweave calls to collective-based MPI libraries into AMT execution, which I'll talk about later. And just as a side note, we've actually found that for some applications, the desire to checkpoint their application without intensive application-specific thought process of what data needs to be saved and how to represent it as like an HDF file or a similar application-specific format, can actually be a backdoor to introducing the set of libraries in such a toolkit. If you can tell people, yes, just add serializers or puppers for for all of your types, and then call this one function from our library, and checkpoints will get written out, and you can restore those and resume execution later. That's a good starting point for telling them, oh, hey, you have these serializers now, so it's really easy to make messages out of these objects, and it's really easy to migrate these objects around to support load balancing. So I'm going to get into some of the execution model and implementation ideas. Just to give a brief overview, the general execution model of VT is very similar to that in Charm++. There are messages in a dedicated structure or class types that get delivered to handler functions, which could either be a general function on a node, or they could be member functions of particular target objects. So one of the implementation challenges in runtime systems like Charm++, and from what we can tell, HPX as well, and as well as lower layers like GasNet or Converse, is that all of the handlers have to be registered in some fashion on every node, and that registration has to be consistent, meaning that the identity of a handler on node 1 has to be the same as the identity on node 7, so that a message saying run handler 22 gets what it's asking for. So one challenge that we've observed is that manual registration of handler functions is sometimes error prone. It sometimes demands big contortions of the programming model in terms of pre-processing. And it's often not exactly cleanly composable across separately developed modules of an application, because the registration logic in each of those modules is going to have to be called in turn from whatever root. And just as an implementation challenge, potential solutions to registration have to deal with function addresses being different across nodes. So you can't just send a function pointer because of address space layout randomization, or just linking and loading differences from one process to the next. So there are a variety of potential solutions out there. So Charm++ does code generation from an interface file to support registration at startup, but it requires an extra step during compilation and during development to write out those interface files. And it also means that when you're putting together the application, you have to make sure that there's a proper tree of the interfaces between all of the modules to make sure everything gets imported correctly, which can be finicky at times. So another possible approach is to try to match the name or the symbol of some function or method at runtime based on various kinds of introspection. This relies on non-standard features that some C++ implementations might have and others won't, and it can be fragile. With large templates, you might run into symbol size limitations. You could also just run into the symbols being excessively large to deal with at runtime. So in the future, we'd like to see something possibly built on reflection that could ease a lot of this. But for the time being, we've actually developed a way using very nearly standard C++ to do this entirely automatically and statically, using some tricks of template instantiation and the defined initialization order of static variables related to them. Just going to check that there's, okay, yeah. So this particular implementation has been found to work across a very wide range of systems that we've targeted. So GNU, C++ going back to 4.9, Clang going back to 3.9, and relatively widely available versions of the Intel and NVIDIA compilers as well, and without any special linker dependencies. We don't require GNU LD versus Gold or LLVM or whatever either. And this technique is compatible with C++11. So in this particular piece, we're not relying on any C++14 features. As you can see here, we have a message send giving the message type and then the handler argument. And the handler is just defined as some bare function that takes a message as an argument and it has code to execute on it. And we give a destination and the message that's actually going to be passed. And the template behind this send function actually calls into registration machinery that creates a static registry at compile time that during process initialization, before any of the code in main can potentially depend on it, will register each of those handlers that gets referenced anywhere in the program and make sure that there is a unique and mostly deterministic identifier, an index number associated with each one of them. So that registration occurs during what the C++ standard terms dynamic initialization of static variables. Notionally at load time, it can potentially be deferred. But the important point here is that this is entirely composable, that two pieces of code that were developed independently of each other with no consideration can both use message sends referencing their own handlers, and all of the registration will happen automatically without the application even having to call any special initialization or per module registration function itself. So we've found this to be highly stable and simplifies a lot of the implementation and usage by developers. So for details of this implementation, we give some of the implementation code in a paper we have upcoming at the EXA MPI workshop at SC20, or we can point you to where in the VT code base this is implemented. And we potentially will separate this out as a standalone library that could be used by others as well. So the execution or programming model of VT is based on what we call termination detection using epochs. So these can be basically, they represent the closure of all the work generated by a set of initial messages sent during some particular interval. So you can ask, the programmer can say, send one message to the next rank in a ring, and that will pass messages to the ring handler going one by one around all the processes. And this run and epoch rooted call will spin the scheduler and only return after all of the causally related messages in the chain have been processed. On a different note, there's also the run and epoch collective, which the rooted version, we started on rank 0 and only made that call on rank 0 to start the send. In the collective version, we start it from the send, but we capture the full set of messages that way. So it's just slightly different expressions of the structure. So what that's actually doing behind the scenes is it's creating one of these epochs that the runtime system is going to keep track of, activating it, running whatever function was passed in to generate the initial set of messages, deactivating it, telling the runtime system that the initial set of messages has all been generated. And so if that the closure of messages that results runs dry, then we're done, and then runs the scheduler until that actually happens. So this is, for those of you familiar with Term++, kind of a scoped version of quiescence detection, where we can talk about particular sets of messages rather than everything happening in the system all at once. For time, since it looks like this is running kind of long, I'm going to skim over details of this a little bit. But often there's some dependencies that that need to be followed based on the work created by any given handler. So we use the chaining of these epochs together to create that structure, but while maintaining asynchrony. So this can be kind of comparable to a chain of futures, but we avoid some of the overheads of tracking the entire execution tree that you would need with futures by just counting up messages within each of these scopes and synchronizing only across the scopes rather than across the individual messages. So, excuse me. So we can make one epoch and add some work, and then following that, we can chain additional work onto it. So we've built the Empire application. We've ported parts of it to run on this execution model using VT. So it's an electromagnetic plasma physics simulator, and it has load imbalances from PIC particle distributions both initially and as their distribution changes over the course of execution. So most of the code in Empire is still implemented in MPI, and we've maintained the ability to have both an MPI and a VT implementation of PIC in Empire that have the same calling code without any awareness of whether it's going to run as MPI or SPMD or asynchronous code on VT. So the agnostic time stepping code makes calls to a front-end implementation that just says take various steps of the execution logic. And in the VT implementation, so in the MPI implementation, these are each SPMD operations that are complete by the time the function returns. In the VT implementation, these are instead functions that send messages to backend objects that are over-decomposed in these chained epochs, and they make sure that the dependencies are satisfied in the order that the various handlers for those messages get processed. So going from there, one of the challenges that we saw in working with closely coupled AMT and SPMD execution is that one often wants to be able to run some MPI library that has collective or communication operations that needs to coordinate across processes. But this might need to be invoked from asynchronous code. So we've developed a protocol that can actually arrange for the runtime system to set up to call a coordinated choice of which MPI-based operation to run at any given time, and have it all start collectively, even in the midst of broader asynchronous execution. So one just example of how this could otherwise be problematic is if you have two handlers, foo and bar, and you do asynchronous broadcasts to each of them, but you want each of them to do ultimately call an MPI reduce, you need to make sure that those actually get run in the same order across all of the nodes and meet the application's intentions. So I'm going to skip over the details of this because I'm running long here. But the broad thrust of this is that we've developed a consensus algorithm that can pick out one of however many such calls have been set up by the application code and make sure that ultimately a common chosen application or operation across all processes gets run at the same time, and then execution of asynchronous tasks resumes. So I'm going to give a brief discussion of some of the things we've done with serialization, also to move forward implementation techniques, and this is mostly in the checkpoint library, so it can be shared across any other runtime system as well. So first is our handling of polymorphic objects, so hierarchies of classes that have virtual methods and need different behavior and might contain different members depending on which class is instantiated. This is a problem that's come up in various settings and it poses challenges. Other existing techniques in POP and Boost Serialize use explicit registrations of different types with some sort of string or other compile time introspection to come up with a string to register the classes, which is, of course, error prone or implementation dependent. And for templates, this could also be difficult and expensive because those representative strings could especially get very large. And you really want to avoid doing that like on a per instance basis. So we use the same static registration pattern that we discussed earlier for handlers to do the same thing for types in the polymorphic class hierarchy. And this generates unique consistent identifiers of every type across all the ranks in a job. We add one line of declaration to each class involved in the hierarchy. And we do some explicit instantiation to make sure everything gets put together properly. So in the base class, the user just has to declare that this is the root of some hierarchy of classes. You don't have to specify the type name. You don't have to specify a string or an integer identifier or anything like that. You just have to declare it. And then in the derived class, each class has to specify what its parent class is, so what it was derived from. So we have these two classes B and C that both derive from A, so they specify that. And then in the class D that might have a pointer to one of these, it's a pointer to A, the base class, but it instantiates C, one of the derived classes. And we can automatically serialize that and make sure that it will reconstruct an instance of C during unpacking. So the other cool thing we've done with in support of serializers is we've implemented a sanitizer akin to address sanitizer or undefined behavior sanitizer that compilers have. So this is a guardrail against the fact that serializers can be very error prone to maintain and to test because the mistake of leaving some new member out of a serializer is the same mistake as leaving it out of a unit test. If you don't keep that up, then it can make difficult to find bugs. So reflection in C++ may ease some of this, but it might be many years before we can rely on that in compilers. So our prototype solution is basically a compile time pass that generates instrumentation that gets inserted during serialization. And then you can run either your application or your unit tests. And at runtime, it will report which serializers did or didn't at least look at every member of the classes covered. So I'm going to skip the implementation details because I'm out of time here, but we can talk about this offline. So just one application result here in Empire. We've benchmarked this, the MPI version and the VT version of a so-called BDOT problem, which is a standard diagnostic for plasma codes on 900 nodes, so 1,800 processes. And we got an overall 2.5x speed up for the application as a whole over the 1,600 time steps done here. So the spikes at every 100 steps in the VT implementation are load balancing, and you can see some other spikes that are mostly system noise. This cluster was particularly noisy. And in the MPI implementation, you can see the wildly varying time per time step because of interruptions to the job processes that the asynchronous execution of VT mostly flattens out because nodes aren't going to be as sensitive to the delays from processing on other nodes. So in conclusion, we're working on this AMT runtime VT that provides incremental value to application developers as they adopt it for any given segment of their application. You can modify one piece at a time, keep everything else in MPI, and not have to go through big contortions to get everything working. The serialization in Checkpoint that we've built is a nice standalone piece, and it's a good introduction to the overall toolkit for users, and it's something of a Trojan horse in that it supports adoption of VT down the line. And we're moving this into production applications in use in Empire. So I will stop there and invite any questions.
All right, thanks, Phil. I don't see any questions on the Google Doc just yet. We have time for a couple. Oh, sorry, there's one from Eric. Do you want to go ahead and ask that?
Do you want to take that in the afternoon? It's about load balancing.
Yeah, if it's load balancing focused, here, I'm going to stop sharing the screen for a moment just so that I can see.
Okay, yeah, let's defer that question for now then until the load balancing talk. Does anyone else? We have time for a couple questions if they're relevant here. Those will move on. Okay, well then if you think of any, we can just consolidate them into the talk you'll give later today.